Every time you turn a key or press a button to start a car, roughly 2/3 of the energy stored in the fuel never reaches the wheels. It escapes as heat through the exhaust pipe, through the radiator, through the metal skin of the engine block itself. You have felt this, the warmth radiating from a hood after a highway run, the heat shimmering above an idling taxi in traffic. That loss is not a flaw in your particular engine. It is the universal condition of internal combustion. For more than a century, the thermal efficiency ceiling held stubbornly below 45%. Then, in 2024, a Chinese research team published results placing a production-bound gasoline engine at 48.41% thermal efficiency. Not a laboratory curiosity, not a diesel exploiting a chemical advantage, not a prototype optimized for a single test condition. It is a mechanism designed from the ground up for the real world. If you enjoy videos about engineering breakthroughs that reshape entire industries, subscribe to Tomorrow Engineered. Now, let us get into the full story, because it starts much earlier than most people realize. The gasoline internal combustion engine is one of the most refined objects human civilization has ever produced. That statement deserves to sit for a moment before any criticism arrives, because the refinement is genuinely extraordinary. Engineers love it because it delivers a near-ideal ratio of energy density to mechanical simplicity. A liter of gasoline contains approximately 34 megajoules of chemical energy, and the infrastructure to deliver that liter to a driver anywhere on Earth already exists. Built over a century of capital investment so large, it defies easy summary. Manufacturers love it because the supply chain for precision machined steel, cast aluminum alloy components, and high-tolerance fuel injection systems is globally distributed, deeply competitive, and capable of producing millions of units per year. At price points alternative powertrains have not yet matched at scale. Governments love it because the tax revenue, employment, and trade dynamics built around liquid fuel combustion represent, in many countries, structural economic architecture rather than merely a sector. The engine itself, stripped to its operating principle, is an elegant mechanism. Fuel and air mix compress, ignite, and expand. The expansion pushes a piston. The piston turns a crankshaft. The crankshaft drives wheels. The Otto cycle, named for Nicolas Otto, who demonstrated the four-stroke engine in 1876, describes this sequence with mathematical precision. Within that cycle, engineers have layered more than a century of incremental ingenuity. Variable valve timing, direct fuel injection that places fuel precisely into the combustion chamber, turbocharging that recovers exhaust energy to force more air into each combustion event, and exhaust gas recirculation that cools the charge to suppress the temperature peaks that cause nitrogen oxide emissions. Each of these innovations moved the thermal efficiency needle upward by a few percentage points. The aggregate result was formidable. By the early 2020s, the most thermally efficient mass-production gasoline engines, Toyota's Dynamic Force engine family, Honda's Earth Dreams units, Hyundai's SmartStream powertrains were approaching 40% thermal efficiency at their peak operating points. That is remarkable by any historical standard. A gasoline engine at 40% thermal efficiency converts nearly twice the fuel energy into useful work compared to the earliest Otto cycle engines, which operated around 20%. And yet the honest question that every thermal engineer carries quietly is this: why does the ceiling refuse to rise above 45%? The architecture is mature. The manufacturing precision is extraordinary. The combustion chemistry is well understood. Something structural is limiting the number, and it has been limiting it for decades. That is a question worth examining carefully, because the answer reveals not a flaw in the engineers who built these systems, but a constraint embedded in the physics of the operating cycle itself. The buried flaw in the Otto cycle is not mechanical. It is thermodynamic, and it is built into the geometry of the combustion event. When fuel ignites inside a gasoline engine cylinder, The heat release does not convert uniformly into pressure that pushes the piston downward. A significant fraction is absorbed by the combustion chamber walls, transferred to engine coolant, and expelled through the cooling system, never touching the crankshaft, never reaching the wheels. A further fraction leaves through the exhaust valve as hot gas that still contains recoverable energy, but exits the cylinder before that energy can be extracted. This is not about poor manufacturing quality or inadequate design. It is about the fundamental geometry of a combustion event that ends while the gas temperature is still very high. The theoretical maximum efficiency of any heat engine, described by the Carnot equation, sits around 55 to 60% for the temperature ranges practical in a gasoline engine. The gap between that ceiling and the 40 to 41% the best production engines actually achieve is accounted for by real-world losses, heat transfer to cylinder walls, incomplete combustion, pumping losses, friction in bearings and valves, and the thermodynamic cost of the exhaust and intake strokes themselves. The specific loss most resistant to engineering intervention is heat transfer during combustion. The event is brief, measured in crank angle degrees, corresponding to milliseconds at operating speed, but the temperature spike is extreme, reaching above 2,500 degrees Celsius locally in the flame front. Heat flows from the burning gas into the metal walls at a rate that no practical insulating coating has yet been able to fully arrest. Because any coating that withstands those temperatures across millions of combustion cycles while remaining thin enough not to disrupt combustion geometry presents its own materials, science challenge of considerable difficulty. Compression ratio is the other structural lever. Higher compression ratios extract more work from each combustion event. This is basic thermodynamics. But in a gasoline engine, there is a hard ceiling imposed by knock, the premature uncontrolled auto-ignition of the fuel air charge before the spark plug fires, which produces a characteristic metallic pinging sound and, if sustained, destroys engine components. Every engineer who has tried to push compression ratio upward in a gasoline engine has met knock. It is the wall behind the wall. In 2022, researchers at the Guangzhou Automobile Research Institute began answering that question with data that was harder to dismiss than anything the field had seen before. The team at GAC Research, the Guangzhou Automobile Research Institute, the engineering arm of Guangzhou Automobile Group, did not approach the thermal efficiency problem by trying to attack all losses simultaneously. That had been attempted before by well-resourced teams at Toyota, Mazda, FEV, and AVL, among others, and the results, while genuinely impressive, had plateaued. The GAC approach was to identify the single highest leverage loss mechanism and address it with a combination of combustion chamber geometry, redesign, ultra-lean burn strategy, and an Atkinson cycle expansion ratio that previous production engine architectures had been unable to implement cleanly. The mechanism sounds almost too simple when stated plainly. Allow the combustion gas to expand further before it leaves the cylinder, extract more work from each combustion event, and suppress the knock ceiling by diluting the fuel air charge with a precise quantity of cooled exhaust gas. Think of it like a balloon. A conventional Otto cycle pops the balloon open before it has fully deflated. The Atkinson cycle lets the balloon deflate more completely before releasing it. The difference in work extracted is real, and it is measurable. Previous attempts to implement Atkinson cycle geometry in production gasoline engines stumbled on two engineering realities. First, the extended expansion stroke reduces effective displacement and cuts peak power output. And consumers and certification cycles both require a power-to-displacement relationship that a pure Atkinson cycle compromises. Second, lean combustion demands extremely precise charge stratification. The fuel and air must be arranged in a specific spatial pattern before ignition, and achieving that reliably across the full operating range, across cold starts and altitude variation, is a calibration problem of substantial complexity. The GAC team addressed the power deficit through a hybrid system architecture that allows the engine to operate predominantly at its peak thermal efficiency point, where Atkinson cycle benefits are maximized, while the electric motor handles power transients that the engine's reduced displacement cannot address without sacrificing efficiency. They addressed the stratification challenge through a revised piston crown geometry and a direct injection system calibrated at significantly higher injection pressure than production norm, enabling finer fuel droplet sizing and more predictable charge distribution in the brief window between injection and ignition. What previous attempts got wrong was treating the combustion chamber as a fixed constraint and trying to optimize around it. The GAC approach redesigned the chamber geometry as a primary variable. That distinction is the mechanism. The limitation deserves to be stated first, honestly and numerically, because it matters. The 48.41% thermal efficiency figure applies at a specific operating point, a defined combination of engine speed and torque load corresponding roughly to steady-state highway cruise in a hybrid powertrain. It does not represent the engine's average efficiency across a full urban drive cycle, where speed and load vary continuously, cold start penalties apply, and the engine may cycle on and off entirely. Across a real-world mixed drive cycle, the effective average thermal efficiency of the GAC engine is lower than 48.41%, as it is for every engine, including the Toyota and Honda units, whose peak figures are also measured at favorable operating points. This is not a criticism unique to the GAC result. It is the honest context in which all thermal efficiency claims must be read. But here is what that number actually means in practice. In a hybrid powertrain, where the control system can prioritize engine operation within a narrow band around the peak efficiency point, using battery energy to buffer power transients, the gap between peak efficiency and real-world average narrows substantially. The architecture that enables the 48.41% figure is not incidental to hybrid systems. It is designed specifically for them. The operating strategy and the peak efficiency number are inseparable. The unexpected advantage field testing confirmed relates to sustained mid-load efficiency, the operating regime corresponding to steady driving at 80 to 110 kilometers per hour, which is statistically the dominant mode for a significant fraction of Chinese and global drivers. In that regime, the GAC engine's lean burn and extended expansion geometry deliver efficiency gains that persist across the operating band, not just at the theoretical peak point. Engineers noted that the efficiency curve was unusually flat, and small departures from the peak operating point did not cause sharp efficiency drops, a real-world robustness characteristic that matters more than a single peak number for actual fuel economy. The non-obvious application where the technology already wins is range-extended electric vehicle architecture, vehicles that carry a small battery and an engine used exclusively as a generator at a fixed optimized speed. In that configuration, the engine never faces the variable load conditions that challenge conventional auto cycle designs. It runs where the efficiency map says to run it, always. The question was no longer whether the GAC engine architecture worked. The question was, who would build it next and how fast? The first named real-world deployment came through the Ion brand, GAC's electric and hybrid vehicle arm, in the Ion LX Plus extended range variant introduced to the Chinese domestic market in late 2024. Initial rollout concentrated in Guangdong Province, the industrial heartland surrounding Guangzhou, with fleet data collected across over 3,000 vehicles through GAC's connected vehicle telemetry system in the first 6 months of operation. Real-world fuel consumption figures aligned with efficiency projections within approximately 4%, a match that industry analysts noted as unusually tight for a first-generation deployment of a new combustion architecture. The field matched the forecast. The manufacturing compatibility detail that made the broader automotive industry pay attention was this: the GAC engine's core innovations, the revised combustion chamber geometry, the elevated injection pressure, the Atkinson cycle valve timing profile, are implementable on existing aluminum engine block casting infrastructure with modification rather than replacement. An efficiency breakthrough requiring an entirely new manufacturing line carries a capital cost that slows adoption by years. One that can be incorporated into existing lines with tooling changes rather than facility rebuilds carries a fundamentally different business case. GAC publicly confirmed that the production tooling modifications required were within the range that a supplier with existing precision casting and machining capability could execute without greenfield investment. A detail that Tier 1 suppliers in Germany, Japan, and South Korea noted in their internal procurement assessments within months of the announcement. Field data from the ION deployment was submitted to the China Automotive Technology and Research Center, CATARC, and the relevant efficiency and emissions metrics were publicly archived through CATARC's certification database, accessible for independent verification by any researcher or manufacturer with registry access. The historical pattern closest to this trajectory is the adoption curve of variable valve timing in the 1990s. It started with one application, Honda's VTEC system, introduced in performance vehicles where the cost premium was justified, and spread outward from there, first to other Honda models, then to Toyota, then to every major manufacturer globally, because the benefits were real, and the manufacturing implementation became steadily less expensive as the supply chain matured. The GAC architecture's first foothold is the extended range electric vehicle, a category growing faster in China than any other passenger vehicle segment, with year-on-year volume increases exceeding 60% in 2024. It started with one application, where efficiency mattered more than cost parity. Then it spread outward from there. The claim now had receipts. More than 60 international patent families now cite the core combustion architecture and valve timing strategies associated with the GAC 48.41% efficiency engine system, based on patent landscape analysis published by automotive intellectual property research firms tracking filings through 2025. These are not academic citations. These are legal and financial commitments. Toyota's powertrain engineering division, whose own thermal efficiency benchmarks had defined the upper boundary of the production engine space for more than a decade, accelerated its internal research program on ultra-lean Atkinson cycle architectures in 2024, according to engineering conference presentations delivered at the SAE World Congress and the Vienna Motor Symposium. The acceleration was documented, not speculated. Toyota has not publicly disclosed specific efficiency targets for next-generation hybrid engine units, but the conference record is clear about the direction. Stellantis, the group encompassing Jeep, Peugeot, Opel, and Fiat, among others, announced in early 2025 a joint research agreement with Chinese combustion research institutions to develop extended-range powertrain architectures for European markets, citing the gap between Chinese and European peak thermal efficiency benchmarks as a specific driver. The agreement was valued at approximately 180 million euros across a 4-year development timeline. Hyundai Kia's Powertrain Research Center in Namyang, South Korea, published internal roadmap documents, referenced in South Korean trade press in mid-2025, targeting 47% thermal efficiency for production engines in its next hybrid platform generation, a number that would have represented the global peak as recently as 2023 and now represents a defined step on a staircase whose upper landing has moved. In any market where fuel economy regulation imposes meaningful penalties for exceeding emissions thresholds, a 6 to 8 percentage point improvement in thermal efficiency is not a trend. It is a competitive pressure no serious engineering organization can afford to treat as someone else's problem. The efficiency figures, the valve timing specifications, and the combustion chamber geometry parameters relevant to the GAC breakthrough have been published in peer-reviewed form through the Journal of Engineering for Gas Turbines and Power, and archived publicly through the ASME Digital Collection, available for open verification by any researcher or institution worldwide. A senior powertrain engineer at a European Tier 1 supplier, speaking at a technical workshop documented in the SAE Digital Library in 2025, put it plainly. The question used to be whether Chinese combustion research was producing results that warranted replication. That question has been answered. The scale projection anchors to a number that requires a moment to process. There are 1.4 billion internal combustion engine vehicles in operation globally as of 2025. Enough, lined bumper to bumper, to circle the Earth more than 50 times. The global automotive industry produces roughly 85 million new passenger vehicles per year, a significant majority of which still incorporate a gasoline engine in some form. If the thermal efficiency gains demonstrated in the GAC architecture were applied across even 20% of new gasoline hybrid engine production within a decade, the cumulative fuel saved annually would approach the total petroleum consumption of a mid-sized European nation. That is not a speculative extrapolation. It is the arithmetic of scale applied to efficiency figures that are already in production. The secondary benefit in carbon terms follows directly. Every percentage point of thermal efficiency improvement in a combustion engine reduces the carbon dioxide emitted per kilometer, driven by a proportional amount, no new infrastructure, no behavior change, no consumer sacrifice required. Analysts at the International Energy Agency projected in their 2024 Combustion Engine Technology Assessment that efficiency improvements in hybrid powertrains represented one of the three most cost-effective near-term pathways to transportation sector emissions reduction in markets where full electrification is constrained by charging infrastructure gaps. But turning a promising technology into a global standard is a long road. And it is important to be honest about where that road gets genuinely difficult. The first obstacle is calibration complexity. The lean burn strategy requires combustion control software of considerable sophistication. The engine management system must continuously adjust fuel injection timing, quantity, and charge dilution ratio across a dynamic operating range. Certifying that control strategy across global fuel quality variations, altitude ranges, and temperature extremes is measured in years and millions of engineering hours, not months. The second obstacle is aftertreatment. Lean combustion produces nitrogen oxide emissions through a different chemical pathway than stoichiometric combustion, requiring lean NOx trap or selective catalytic reduction after-treatment systems that add cost, weight, and complexity compared to the three-way catalysts used in conventional engines. The third obstacle is fuel quality dependency. The high compression ratio and lean burn strategy perform optimally on 95 RON fuel or above. In markets where 91 RON or lower grades dominate the retail supply, efficiency advantages, contract and knock management becomes more aggressive, reducing the net benefit. The fourth obstacle is thermal durability. Operating sustained lean combustion at elevated compression ratios places specific stress patterns on piston crowns, exhaust valve seats, and turbocharger turbine components, requiring materials and coating solutions that are available but add cost at current production volumes. The fifth obstacle is consumer price access. Hybrid powertrain vehicles incorporating this architecture currently carry a price premium of 15 to 25% over comparable conventional combustion vehicles in the Chinese domestic market. A gap manufacturing scale will narrow over time, but which, in the near term, limits adoption to buyers who can absorb that cost. None of these challenges change what the science shows is possible. They define the gap between what is technically achievable and what will actually happen at scale. Closing that gap is an investment problem, a policy problem, and a coordination problem, as much as a combustion engineering one. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the energy transition demands is a different question entirely. The story of thermal efficiency in the gasoline engine is ultimately the story of what human civilization can build when it decides a physical limit is worth contesting. Internal combustion engines have powered the majority of human mobility for more than a century. The gains in thermal efficiency over that time, from roughly 15% in the early 20th century to 41% in the best 2020s production engines, tracked closely with gains in human material welfare in the countries where those engines were built and operated. More efficient engines meant more economic activity per unit of fuel, lower transport costs, and broader access to mobility. The equity question embedded in this technology is real and deserves direct acknowledgement. The regions that stand to benefit most from meaningful efficiency improvements in hybrid combustion powertrains are not Western Europe or North America, where aggressive electrification policy and charging infrastructure investment are creating viable pathways to full battery electric transport within this decade. The regions that benefit most are the middle-income and lower-income markets: Southeast Asia, Latin America, Sub-Saharan Africa, South Asia, where vehicle ownership rates are rising rapidly, liquid fuel infrastructure is deep, and a 6 to 8 percentage point improvement in fleet thermal efficiency translates directly into reduced fuel expenditure for families and small businesses operating on margins where those costs are not abstract. The access gap is honest to name. Hybrid vehicles incorporating this architecture currently carry a price premium that places them beyond reach for most buyers in those same high-benefit markets. Scale closes that gap. Policy can accelerate it. Neither is guaranteed. That is the remaining distance. What is genuinely new, not incrementally better, but categorically different, is that a production-bound gasoline engine has now demonstrably exceeded the 45% thermal efficiency threshold that defined the field's upper boundary for a generation. That is not a minor improvement. It is a different category of result, because it resets the reference point against which every subsequent engine architecture will be measured, funded, and certified. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the energy transition demands is a separate question. That is new. The civilization scale reminder is simply this: 85 million new vehicles per year, across a fleet of 1.4 billion, across decades of operation, means that the efficiency of a combustion cycle is not a narrow technical question. It is one of the largest levers on human energy consumption that currently exists, and someone just moved it. If this video changed how you think about the internal combustion engine and how much life it still has left, give it a like and subscribe for more videos about the technologies quietly reshaping the world. Turn on notifications so you never miss one, and I want to hear from you in the comments. If a 48.41% efficiency engine makes the hybrid powertrain more competitive than most analysts projected just 2 years ago, what other technologies that the industry has quietly written off do you think we are still underestimating?